Hello wonderful person, this is Anton, and today we're discussing everyone's favorite topic, Dyson spheres and megastructures. Or I guess it's my favorite topic when it comes to various potential alien civilizations and how we can one day maybe detect them. And specifically we're focusing on this new paper that might have discovered a completely new way of discovering these alien megastructures and thus potentially discovering some sort of an advanced alien civilization by looking at how the star should in theory transform if a megastructure is built around it. And the study itself, as always, can be found in the description below, with some of the major discoveries here suggesting that these unusual megastructures actually have a very interesting potential to completely transform a star, even making it live much longer. So let's discuss this in a little bit more detail, starting of course with a brief overview and a little bit of history. As you might already know, the idea of Dyson spheres was a kind of a thought experiment of this wonderful person, Freeman Dyson, a theoretical physicist who unfortunately passed away last year. With the thought experiment itself essentially suggesting that, in theory, to basically get as much energy as possible, some sort of an advanced civilization would probably use the entire star by capturing the energy from the star and do so by basically wrapping something around the star itself. In essence, producing something that's maybe similar to what you see right here. This would be an example of what's known as the Dyson ring, sometimes also referred to as a Dyson swarm. But in order to optimize the capture of energy, you would obviously want to produce some sort of a Dyson sphere. And his thought experiment led him to believe that these particular spheres would then emit a very specific type of infrared radiation simply based on the absorption and emission of energy, and this type of infrared radiation should be detectable by some of the modern telescopes. Although later on, scientists calculated that in order to even build this sphere, you would require more mass and more material than we actually have in the entire solar system. Or in other words, even if we were to break apart every planet and every asteroid and then somehow wrap all of this around the sun, we would still be lacking a lot of the materials needed for this kind of a structure. And on top of this, a sphere itself would not be physically stable, both for gravitational reasons and because of the pressure from the sun. So here, as an example, if I take a hypothetical sun and place a hypothetical Dyson sphere around it, and then run the simulation, you'll notice that pretty much right away all of this sort of falls apart and starts to orbit in a somewhat different fashion. It might be easier to visualize it if I change this to velocity measurements. So here the actual orbital parameters are very important, and because of this it's actually a lot easier to build some sort of a ring or some sort of a swarm of rings. And so a set of rings around the sun would be a much better way of capturing all of this energy, and would also require a lot less material and thus be a lot more feasible. And just like I mentioned, these structures would then also produce a very specific type of infrared emissions simply based on the amount of energy captured from the sun, and would also most likely produce various types of dimming effects. And that's basically because they would be blocking some of the light coming from the star itself. And this is how back in 2015, some of the amateur astronomers, along with some of the scientists, realized that at least one star, the star known as KIC 8462852, also known as Tabby star, was actually producing some unusual dimming effects that could in theory be explained by a megastructure. This was the news back in the days, but later on the scientists have also realized that, well, first of all, it wasn't really producing these infrared effects, the ones that we kind of expect from a typical megastructure, but also the emissions were much more likely explained by something more natural, such as a swarm of really massive comets, or more likely, and this is actually the most recent explanation, some sort of an uneven ring of dust that seems to be in orbit at just the right angle, which seems to block the star occasionally. Moreover, in the last few years, scientists have identified several other similar stars, and so this is most likely not an explanation that requires some sort of an advanced alien technology. It seems to be best explained with just natural environment and just the right angle of observation. Nevertheless, the scientists, especially the ones associated with SETI, the search for extraterrestrial intelligence, still want to find as many possible ways of finding these structures as possible. And so obviously just seeing the dimming effect is not enough. And even detecting infrared emissions might also not be enough to prove something, because these infrared emissions could also be coming just from the object itself, like for example a comet, being heated up by the sun and thus emitting certain types of infrared radiation. And so this new paper proposes a third way, and a very original way, to potentially discover these objects and to also potentially transform a star in a way that nobody has really thought of before. It's actually a really interesting and very intriguing proposition. But the proposition is self-suggesting that this type of a structure will actually dramatically affect the temperature of the star, causing it to first of all cool down, but then also start growing in size. Something that nobody has really considered before, but the explanation here definitely makes sense. So how exactly would any of this work? Well, in essence, this would work on the principle of energy feedback, or basically a lot of energy being reflected back into the star itself. And so in theory, if these structures do exist, the material that they're made from might actually reflect just a little bit of light back into the star. And also some structures might be actually made specifically to reflect the energy for the reason I'm going to discuss in a few minutes. And as all of this energy comes back into the star, it actually influences some of the conditions and some of the balance that usually forms inside a typical star. Now, in one of the previous videos about the discoveries from the Parker Solar Probe, we've already discussed the inner structure of our Sun and how some of this works. You can learn more about this in one of the previous videos. But in essence, there are two very specific areas in our Sun that are really important for this particular activity. There's the convection zone, where a lot of the material sort of circulates based on the temperature difference between the lower layer and the higher layer. And then there is the radiative zone, where everything just goes in one direction, with the energy itself generally moving really slow. And generally whether these areas form and how they form really depends on the total mass of the star. Also interestingly, the less massive stars, so in this case red dwarfs, or the stars that are roughly around 30 to 40% the mass of the Sun or even less, will only have the convection zone inside of them and will produce absolutely no radiative zone at all. And because of this, they end up mixing all of the material inside the star for a very long time, allowing the star to feed continuously. Whereas in larger stars like our Sun, because of the one direction of the radiative zone, eventually the star is going to run out of energy and will actually start transforming a lot sooner. So because of this, stars like our Sun live much shorter than, for example, a typical red dwarf. Whereas in stars that are more massive, such as the nearby Sirius, the upper layer right above the convection zone also produces another radiative zone with tremendous amounts of energy being released by the star itself, which then produces a lot more brightness, a lot more solar winds, and basically a lot of everything. And because of this, these stars also don't really live as long. But what exactly happens when some of this energy returns back into the star? Well, as you can probably imagine, it really depends on the mass of the star and on the actual areas inside the star. So for stars that are smaller in mass, so for a typical red dwarf, since they mostly have convection happening on the inside, all this energy then reaches all the way down to the core of the star itself, where a lot of the hydrogen is being fused, producing the energy. And inside a typical core of a typical star, what essentially ends up happening is a kind of a balance. Here, the energy from the fusion is basically counterbalanced by the gravity of the star. So if you add a little bit of mass, for example, if you add a little bit more gravity, the star will most likely shrink because the gravity is going to start winning. Whereas if you add a little bit more energy, the pressure from the energy will increase and the gravity will start losing, thus increasing the size of the star. Which is sort of what the scientists believe happened in this case. For a red dwarf with a lot of energy coming inside of it, the actual balance will shift toward energy and will most likely start increasing the size of the star because the gravity is now losing. But because of this unusual expansion, you suddenly have more volume, and that means that hydrogen atoms will not actually be able to fuse as easily. In other words, it decreases the chance for two hydrogen atoms to collide, forming helium, which surprisingly ends up cooling down the star, while also making it slightly larger as well. And interestingly enough, this type of a feedback mechanism will also most likely dramatically expand the lifetime of the star as well, simply because a lot less hydrogen is used in this case, and so in theory the star can survive much longer. As a matter of fact, the calculations here suggest that by having some sort of a feedback that's approximately 50% efficient, a typical red dwarf star can actually double its lifetime, so in this case from 1 trillion years to maybe 2 trillion years. And the main reason the size increases is because the convection zone in this case ends up producing a slightly smaller radiative zone right on top, which then ends up expanding the star slightly larger than before. It's not really doubled in size, but it's increased by about 15% or so. But what's unusual here is that even though the temperature inside the star decreases, on the surface the temperature might remain the same, so visually at least, it would still maybe appear similar in color, or at least in luminosity, but just have much larger size, which would be a telltale sign that something unusual is happening around the star. Then when it comes to more massive stars, such as Sirius or any other star that's A-type or B-type, unfortunately this mechanism doesn't seem to affect them as well. Because of the presence of the radiative zone right on the surface here, it actually prevents any feedback mechanism from affecting the star on the inside. But at the same time, these massive stars also don't generally live as much, and on average they also don't tend to have as many planets either. So these are not as interesting for the search for extraterrestrial intelligence. But when it comes to stars like our own Sun, something really extreme happens in this case. Because of that relatively small convective zone on the surface of the Sun, and because of the feedback mechanism coming from the megastructure, it actually ends up creating another radiative zone right on the surface of a star similar to our Sun. And according to the study, this in theory can actually triple the size of the star as it essentially starts expanding because of the radiative zone that's produced on the surface. And at least in theory, this would also prolong the star life as well. So in some sense, by building something similar and reflective around our Sun, we can maybe provide a little bit more lifetime to it. But it will also expand in size, which means that some planets might be quite dramatically affected by the increase in total luminosity. In this case, Earth might actually become way too hot. So this would be sort of a perfect scenario if one day we want to somehow colonize Mars and would like to have Mars with slightly warmer conditions. The increase in luminosity coming from the Sun would dramatically warm up the red planet. And so in essence, what this paper suggests is that there is a third way for us to potentially detect if something is a Dyson sphere by simply observing the changes in the star itself. For example, that previously mentioned Tabby star. If we detect that the star seems to be slightly larger in size, or maybe has some unusual temperature variations on the surface, well, that would suggest that maybe the star was actually influenced by some sort of a megastructure. And if we then combine this with the infrared emissions and with the dimming effects from the megastructure itself, it could then in theory help us identify if this is indeed what we're looking for, or what SETI is looking for, if this is indeed some sort of a Dyson ring, Dyson sphere, or some other really cool megastructure produced by an alien civilization. And since this technique also proposes a way to potentially extend the lifetime of a star, it's definitely a very intriguing proposition for some sort of a Type 2 civilization capable of producing these grandiose structures. But for now, it's still in the realm of science fiction and in the realm of thought experiments. Even now, we still don't know if this is actually something that some sort of advanced civilization would try to achieve. In theory, maybe it is possible, but some other theories propose something entirely different. There's a video about this as well, but in a nutshell, it actually involves efficiency and evolution. Chances are some advanced civilizations might actually evolve to become so efficient that they don't need to have megastructures. And that's something that I've discussed in one of the previous videos. Anyway, it's a really cool paper. You can check out the paper and the blog post from the main scientists in the description below. And it's definitely a really interesting third sign to look out for when looking for megastructures. But once we learn more, or once we actually find something that resembles one of these structures, I'll make sure to follow this up with another video. Until then, thank you for watching, subscribe if you still haven't, share this with someone who loves learning about space and sciences, and maybe come back tomorrow to learn something else. Maybe support this channel on Patreon by joining a channel membership or by buying the wonderful person t-shirt you can find in the description. Stay wonderful, I'll see you tomorrow, and as always, bye bye.